Okay, so yeah, that's basically those processes in the body. And then now we're going to move on to acids and bases, which we never escape. We learn about them in Gen Chem and they stay with us forever. And apparently this one's a very high yield topic on the MCAT. There's a lot of questions that have to do with acid and base topics. And I'm sorry that this video is so long. Okay, so the Bronsted-Lowry definition of acids and bases, that's the one where the Bronsted-Lowry acids are the proton donors and the bases are the proton acceptors, right? And then the Lewis definition, which is where the bases are the electron donors, and then the acids are the electron acceptors, right? Two ways of thinking about the same thing, except for the Bronsted-Lowry is only for protons, right? And the Lewis is more general. It doesn't have to be a transfer of hydrogens. And they come in conjugate acid, conjugate base pairs. Okay, yeah, so Ka. This is, you remember the equilibrium constant, right? This is the equilibrium constant, but specifically for acids. And so what it's going to have is your products over here, right? Because the acid dissociates. It goes from HA to H plus and A minus, right? And so the products go on the top and the reactants go on the bottom. And so this is just our equilibrium constant, but for acids. Kb is our equilibrium constant for bases. Higher Ka means stronger acid, obviously, because that means there's going to be more H plus in the solution, right? And then the higher H plus there is, if you remember pH, it's the negative log of the hydrogen concentration, right? So, yeah. So if you have more more hydronium ions in there, then it's going to be a stronger acid, higher Ka, stronger acid. Amphoteric substances. Okay, this is a molecule that can be both an acid and a base. So the example that they gave us here is this carbonic acid with H2CO3, right? And then this one is the acid. It loses a proton, and so then this is the conjugate base of carbonic acid. But then this one can also lose its other proton. So now in this equation here, this guy loses a proton and it becomes this guy. So you can see that this same molecule is functioning as a base in this case and an acid in this one. It's called amphoteric. The conjugate base of weak polyprotic acids are always amphoteric. And it specifically has to be a weak polyprotic acid. Polyprotic just means more than one hydrogen. It specifically has to be a weak polyprotic acid because if you have a strong polyprotic acid, then remember it just ionizes completely. So you're not going to have like a conjugate base that still has a proton attached, because that proton is already going to be ionized into solution, like dissolved. So that's why. And also all amino acids are amphoteric, and that is, I think that's because of the amine groups and then the carboxylic acid groups. Okay. So your pH is your negative log of your H plus, and then your pKa is your negative log of the Ka. But if you remember what Ka is, negative log, your Ka was H plus, basically, A minus over HA. Oh wait, and then this is at equilibrium. Remember, because Ka is an equilibrium constant, And so this one never changes, right? This one just tells you what the concentrations are going to be at equilibrium. But if you look here, the only thing in the pKa equation that would change the pH is this hydrogen concentration here, which is the same as what it looks like here. So really pKa and pH are both kind of measuring the same thing. So the pKa, if you looked at it, your pKa is going to give you the pH at equilibrium for that acid. Yep. And so, okay, that's going to come up later. So your buffer solutions are going to have a weak acid plus its conjugate base in roughly equal amounts. And so buffer solutions keep your pH from changing that much, because there's some acid and some base, so it can neutralize any pH changes that come in. That way you can kind of keep the pH pretty steady, and this is really important in the body and the blood. So, for example, in your bicarbonate buffer solution, when you have this acid here, and then normally it goes and it becomes H plus and then HCO3 minus, which is the conjugate base, and then there's some sort of equilibrium here, right? And then the concentration of hydronium is going to determine what the pH is. Let's just say you added some acid. What's going to happen is then, because of Le Chatelier's principle, right? Because now your Q has your Q is bigger than K, so it's going to shift to the left. And so some of those protons, they change back into this H2CO3, right? So there's less of those protons floating around and changing the pH. So the change in pH is going to be really small, because there's these two things present. When you add that acid, it's going to shift things over this way to make it so that whereas normally you would have all the protons from the acid floating in solution, changing the pH, now those protons are being shifted back into this not ionized form, and there's no huge shift in pH. This is really important in body systems. So yeah, and then now this is where you answer your questions. Don't look at the answers. Hee hee. Blah blah blah. Okay, yeah, that was kind of a long video.